everyone, this is Mrs. Snowbeck. Today we are going to do Unit 3, Lesson 3. We're going to learn how to graph cosecants and secants. So by the end, I hope you can say I can graph secant and cosecant, and I can graph the transformations of secant and cosecant. Recall from earlier this trimester that the cosecant of x is equivalent to 1 over the sine of x. And the secant is equivalent to 1 over the cosine. So remember that the way I remember it is the s's do not go together. The c's do not go together. Cosecant goes with sine, secant goes with cosine. So y equals cosecant of x is really equivalent to y equals 1 over sine x. So what we're going to do is think about sine x here. Think about the unit circle. When you have the unit circle, the coordinate right here is 1, 0. This is 0, 1. This is negative 1, 0. And this down here at 270 is 0, negative 1. And so the sine value at 0 radians is 0. The sine value at pi over 2 radians, or 90 degrees, is 1. The sine value at pi is 0, the y value. The sine value at 3 pi over 2 is negative 1. And when we're back at 2 pi, it's 0 again. And so what we're going to do today is fill in a couple of those extra values. And so think about pi over 4. Pi over 4 is right here. That's at 45 degrees, right? Do the hand trick. So bend down your 45-degree finger. So we're going to bend down this middle finger. There's 2 on the left and 2 on the right. And so the coordinate at 45 degrees is, there's not a lot of room here, but it's root 2 over 2, comma, root 2 over 2. That's the coordinate there. So what's the sine value? Root 2 over 2. What is it at 3 pi over 4? Well, 3 pi over 4 is here. So the sine value, this would be negative root 2 over 2, comma, root 2 over 2. So the sine value again is root 2 over 2. By the time we get down here, it's going to be negative root 2 over 2. And over here, it's going to be negative root 2 over 2. Imagine graphing that regular sine curve. Imagine graphing y equals sine x. So you would put a point at 0, 0. You would put a point at pi over 4, root 2 over 2. You're like, where is that? Well, remember, the equivalent to root 2 over 2 is approximately 0.707. So if I graph that, we're going to have a point at 0, 0, about 0.707. At pi over 2, we're at 1. At 3 pi over 4, we're at 0.7 again, and then at pi we're at 0, and so on and so on. And I graph these points, and you can see this is the normal sine curve. It's there in the dashed line. Now let's think about cosecant x. Remember, cosecant is equivalent to 1 over sine. So imagine we do 1 over 0. Can you have 0 on the bottom of a fraction? No, you cannot. That's like an alarm should be going off. This ends up being what's called undefined. Next one, we're going to take 1 over root 2 over 2. Well, remember, you have to get this off the bottom of the fraction, so we're going to multiply by 2 over root 2, the reciprocal. We're going to wind up with 2 over root 2. Can't leave a root on the bottom, so we got to rationalize the denominator. So we end up with 2 root 2 over 2, but the 2's cancel out, so we end up with square root 2. But let's do this. Since we're going to be graphing this, it's kind of hard to know where root 2 is. Plug that in your calculator. The square root of 2 should be approximately equal to 1.414. So I'm just going to put in here, this is approximately 1.414. It's going to be easier to graph later. Next, we have 1 over 1. Well, that's 1. Next, we have 1 over root 2 over 2. Well, we just did that. That's approximately 1.414. Next, we have 1 over 0. Can't have 0 on the bottom of a fraction, undefined. Next, we have 1 over negative root 2 over 2. Well, it simplifies the same as the last one. We just have a negative on the front. So this is going to be approximately negative 1.414. Negative 1 or 1 over negative 1, well, that reduces to negative 1. That one's not so bad. This one's going to be negative 1.414 again, and this one's going to be 1 over 0. Can't do it. So we're going to make that undefined. Now, every time you see the word undefined, you can't have any values at those points. So at radians of 0, I'm going to put a dotted line here. And that's just representing that I can't have any points at 0 radians. The next one I see is at pi. Pi is also undefined for cosecant. So I'm going to put another vertical line here. These are called vertical asymptotes, and it's basically just showing you cannot have any values there. The next one is at 2 pi. So 2 pi is also going to get an asymptote, a vertical asymptote. And you can imagine if we went the other direction, we would have one at negative pi, and we would have one at negative 2 pi. No points are going to be graphed in those locations. Now let's graph some of these other points. So at pi over 4, we have about 1.4. So I'm going to go over to pi over 4 and put a dot at about 1.4. At pi over 2, we're at 1. That's right here. At 3 pi over 4, we're back up to about 1.4. And then we hit our undefined. Then let's keep going. At 5 pi over 4, we're at negative 1.4. That'd be about here. At 3 pi over 2, we're at negative 1. At 7 pi over 4, we're at negative 1.4. Here's what you do. Connect your dots like so, and they are going to approach those vertical asymptotes, but they can never reach them. So they're going to get really close, but they can never touch. And so you can see when you graph the cosecant, it's really a reflection of the sine curve. So the graph of cosecant x is really a bunch of U-shaped branches that are between the adjacent asymptotes. Now what's the period? How long does it take before it repeats? Well, let's see. Let's say we start here, and then there's one U-shaped branch that goes up, one U-shaped branch that goes down, and then here we would repeat. So the period is 2 pi. Domain, this is kind of weird. So the domain is the x values. So how far left and right does it go? Well, kind of forever, but there's these places where you can't have an x value. Anytime you see the vertical asymptotes, I'm going to just highlight them in blue, each of these places, there's no x values. So how do we write that? It's kind of weird. Well, you write it like this. The domain is all x values such that x cannot equal something. What can it not equal? Well, it's at 0, pi, 2 pi, 3 pi, 4 pi. So basically it's any multiple of pi. So x cannot equal n times pi, where n is any integer. So that kind of tells you there's vertical asymptotes where you're not going to have x values. Let's think about the y values, the range. How high up and down can it go? Well, it can go forever up and forever down, but there's this span in the middle where you're not going to get any y values. So the range, it can go forever downward. It can start at negative infinity, but as it comes up, let me just trace it here. As it comes up, the highest it's going to hit is negative 1. So the range goes from negative infinity to negative 1, including negative 1. And also, so I'm going to do union, it can start at positive 1 and then go up forever. So it can include 1 up to positive infinity. And that's the range. Let's try to graph y equals secant x. Remember, secant x is equivalent to 1 over cosine x. So think about your normal cosine curve. Your normal cosine curve starts here, 1 above 0, and heads down to 0 and then to -1. So let's do that. If it starts at 1, and then it goes to 0, and then it goes to -1, and then it goes back to 0, and then it goes back to +1. And in between there, the value at pi over 4 is going to be root 2 over 2 for cosine. What I do is I just do the hand trick and I think about pi over 4. That's really 45 degrees. I bend down that 45-degree finger and I have 2 over here, so it's root 2 on the top. Same thing for 3 pi over 4. Think of the value over there. So if your graph is here, your unit circle, 3 pi over 4 is over here, so it's going to have an x value that's negative root 2 over 2. Then over here at 5 pi over 4, the x value would be negative root 2 over 2. And then over here at 7 pi over 4, it's going to be positive x value, positive root 2 over 2. Also remember that root 2 over 2 is approximately 0.707. So when you look on the graph, you can see here's positive 0.707, here's negative, here's positive. You can see those points coming onto the graph of cosine. Now let's think about secant. Now remember, secant is really the same as 1 over cosine. So 1 over 1, well, that one's pretty easy. That one's 1. 1 over root 2 over 2. Well, we just did that not too long ago. It was 1.414. 1 over 0. Uh-oh, can't have that. That's undefined. Then we have negative 1.414. 1 over negative 1. Well, that's negative 1. 1 over negative root 2 over 2. That's negative 1.414. 1 over 0. Undefined. And here we have positive 1.414, and then 1 over 1 is 1. Let's put vertical asymptotes at our undefined locations. So we have undefined locations at pi over 2. So right here, we get a vertical asymptote. And then we get another one at 3 pi over 2. And then that's all we have in our chart, but you can imagine there's 4 squares here, 1, 2, 3, 4. It's going to continue this way, 1, 2, 3, 4. We're going to have another vertical asymptote at negative pi over 2 and at negative 3 pi over 2. So let's graph secant x. So secant x, our first coordinate goes at 0, 1. So over 0, up 1, here it is. Then our next coordinate goes at pi over 4, 1.4. So pi over 4, 1.4 is about here. Then our next one is undefined. Then our next one is at 3 pi over 4, negative 1.4. So that's about here. Then we're at pi, negative 1, about here. Then we are at 5 pi over 4, negative 1.4, which is here. Then we're at an undefined, which you can see our red vertical asymptote. And then we're at 7 pi over 4, 1.4, and then we're at 2 pi, which is 1. So again, when you connect these dots, you're going to get U-shaped branches. And these U-shaped branches are going to approach those vertical asymptotes, but not touch. And so we're just going to sketch in the rest of them. And voila, you have graphed y equals secant x. What's the period? How far does it go before it repeats? Well, let's see here. If we start with the U-shaped branch that goes up until the U-shaped branch that goes down, that looks like one period. So it goes from negative pi over 2 to positive 3 pi over 2. Imagine if you just shift that 2 boxes to the right, it would go from 0 to 2 pi. So our period is still 2 pi. That's how long it goes before it repeats. The domain, what are the x values? Well, it goes forever to the left, forever to the right. So our domain is all x's such that x cannot equal what? Where are the vertical asymptotes? Well, it seems like they're at pi over 2, right? So every time we hit a pi over 2, we can't have any values, so x can't be at pi over 2. And then think about how far apart they're spaced. They're spaced 1, 2, 3, 4 boxes apart, which is equivalent to pi. So they can't be at pi over 2 or any interval of pi. So think about n can be any integer when n is any integer. The range, let's talk about the range. How high up and down can it go? Well, it can go forever down, but as it comes back up, it's going to stop at -1. And it can go forever up, so it can start here at +1 and go up forever. So it's starting at 1 and going up to positive infinity, and that is the range. So here are the guidelines for sketching graphs of cosecant and secant. Number 1 is you graph the corresponding reciprocal function as a guide. So you're going to graph either like sine or cosine. Then you're going to sketch in the vertical asymptotes, and then you're going to graph in or sketch in the U-shaped branches between the vertical asymptotes. All right, let's see if we can do these a little faster now that we kind of get what we're doing. So the reciprocal function, I'm just going to write this down, reciprocal function for y equals 3 secant x is y equals 3 cosine x. So the first thing we're going to have to do is we are going to have to graph y equals 3 cosine x. Okay, so let's think about the period. Remember cosine, y equals a cosine k x minus b plus d. So the period is usually 2 pi, and we divide it by k. So 2 pi divided by absolute value of k. Well, in this case, there's nothing there in front of the x, and so the period is still 2 pi. Does it reflect over the x-axis? Is the a negative? No. Is there a vertical shift? So the vertical shift would be the d. Nope, I don't see any d in our equation, so no. Is there a vertical stretch or shrink? And the answer is yes, there's a stretch by 3 because your altitude or your amplitude, excuse me, is 3. So let's graph y equals 3 cosine x. Normally cosine starts at 1 above the horizontal. So I'm going to count by ones actually. I'm going to count, this is 1, 2, 3. This is -1, -2, -3. And for cosine, this time it has to have a vertical stretch of 3. So instead of starting 1 above the horizontal, I'm going to start 3 above. And then we go to 0, and then we go to 3 below, and then we go to 0, and then we go to 3 above. So this is what the graph of y equals 3 cosine x would look like. Let's finish off that graph. Here it is. Now our second step is to draw in the vertical asymptotes. So I'm going to, every time we have a hill or a valley, I'm going to separate them. Like I can see right here. I'm going to separate them. Right here, I'm going to separate them. So I have a hill and a valley kind of separated by vertical asymptotes. Now I'm going to draw in my U-shaped branches. So I just reflect those hills and valleys. And I want to approach the vertical asymptotes but not touch. So that blue, the blue U's and upside down U's are the graph of y equals 3 secant x. So a quick recap is number 1, we sketched y equals 3 cosine x. Number 2, we sketched the vertical asymptotes. And then number 3 is we sketched y equals 3 secant x by drawing in the U-sized branches or the U-shaped branches. Let's try number 4. Y equals negative cosecant x, the reciprocal function. The reciprocal function is y equals negative sine x. So the period, think about this equation right here. What's the period of normal sine curve? Period is 2 pi, and that's not going to change here because there's no k, there's no value right in front of the x. Is it going to reflect over the x-axis? Yes, it is, because it's negative sine x. It's like a negative 1 in front of the word sine. Is there going to be a vertical shift? Nope. There's no d in this equation. There's nothing that's going to shift it up or down. Is there a vertical stretch or shrink? No, because the coefficient in front of there is negative 1, and 1 will not stretch or shrink it. So the only thing that's going to happen here is it's going to reflect over the x-axis. Okay, so let's graph our first kind of parent function here. So number 1, we're going to graph y equals negative sine x. Okay, so think about normally sine starts at 0, 0 and goes up to 1. Well, if we are reflecting it, instead of going up, we're going to go down to 1. So let's number off here. This can be negative 1. This can be positive 1. Then we're back up to 0. Then we're up to positive 1. Then we're here back at 0. So I'm going to put a dashed line. I should have done this on the last one too. Usually you put the original with a dashed line. And I'm going to fill in the back side of my graph here, because this isn't actually the graph we're looking for. We're just using this graph to find the graph we're looking for. Okay, now we're going to draw in our vertical asymptotes. So we're going to separate the hills and the valleys. So here's one, here's one, here's one, and here's one. Oh, and here's one too. So there's our vertical asymptotes. So just to write that down, then second we drew in our vertical asymptotes. And now 3 is we're going to actually sketch in y equals negative cosecant x. So remember, to do this, we're just going to flip the hills and the valleys. And we want to approach those vertical asymptotes but not touch. And there it is. Those blue U's are the graph of y equals negative cosecant x. Number 5. So we have y equals secant x minus 3. So we're really going to graph y equals cosecant x minus 3. What's the period? Well, normally a cosecant would have a period of 2 pi. It's still going to have a period of 2 pi. Because there's no k, there's no number in front of the x there that's going to change that. Does it reflect over the x-axis? No, because the number in front of the cosine is just a 1, it's not negative, so it's not going to reflect. Is there a vertical shift? Yes, there is a minus 3 back there, and that minus 3 is going to shift the whole graph down 3. So yes, minus 3. Is there a vertical stretch or shrink? No, because the amplitude was just 1, so there's no vertical stretch or shrink. Let's see if we can graph this function. So the midline has to shift down 3, so counting by ones, this is a graph, or this is a line at y equals negative 3. So let me just count here, negative 1, negative 2, negative 3, if I'm counting by ones. My midline is going to be way down there, okay? Normally cosine starts 1 above that line and goes down. Do we have to change that? No, I don't think we do. So we're going to start 1 above our midline, then we're going to go to 0, then we're going to go to 1 below the midline, then to 0, and then 1 above the midline. And so I'm going to connect these with the dotted. It's not actually my final answer. and then I'm going to continue over here. So there's the graph of y equals cosine x minus 3. Number 2, draw in your asymptotes. Okay, so anytime you have a hill or a valley, we have to separate them. So it looks like here and here. Basically, it's where your points are on the midline. See how we have a point on the midline right here, and right here, and right here. That's where I'm going to draw my asymptotes, is where does your graph cross the midline, basically. Okay, now flip your little hills and valleys. And so you're going to, oops, let me erase that and do it in a marker. Okay, so one's going to go here, one's going to go here, one's going to go here, and then I've kind of got half of one over here. And there it is. And the blue lines then are a sketch of y equals secant x minus 3. Why don't you guys do this? Pause the video and see if you can do number 6, and then unpause when you're done. So you have to think about the reciprocal function, which is y equals negative 1/2 sine x. So does the period change? I don't think so. There's no k, there's no number right in front of the x, so I don't think the period changes. So it's still going to be 2 pi. Reflect over the x-axis, yes, because the a is negative. Is there a vertical shift? No, there's no d. Is there a vertical stretch or shrink? Yes, it's going to shrink by 1/2. Okay, so think about graphing the normal sine curve. Normally the sine curve, let's say this is 1 and this is negative 1. Normally the sine curve starts here, goes up to 1, goes back to 0, so that's normal. But we're going to have to reflect it, and we're going to have to shrink it. So I'm going to erase these points. And I think our first point is still at 0, 0. But then instead of going up, we're going to go down. But instead of going down 1, we go down half as much. So we're going to go to right here. And then back up to 0. And then up to 1/2. And then down to 0. So see how we have a vertical shrink. It's only going up 1/2. I'm going to dot this. And now let's get the back side of that. So we'll have a dot, let's see, right here, right here, right here, right here. Then draw in your vertical asymptotes. Every time it crosses the midline, or anytime you see a hill or a valley, separate them. Okay, there's our vertical asymptotes, and now we draw in our actual cosecant graph. So just reflect the hills and valleys. And there it is. The red stuff is actually our graph. Last one. Will you guys please pause the video and try number 7? When you're done, unpause. So you're going to graph y equals 1 minus 2 sine x. Now I like to rewrite that so it's negative 2 sine x plus 1. That means the midline is going to shift up 1. The period, there's nothing right in front of the x here, so the period's still 2 pi. Is it going to reflect over the x-axis? It's negative there, so yes. Is there a vertical shift? Yes, that's the plus 1 back here. So yes, it's going to go up 1. And then, is there a stretch or shrink? Yes. You have a negative 2 here, so it's going to stretch by 2. All right, let's draw in our midline. Think about where is the midline. Well, the midline is plus 1. So we're going to go up 1. I think I'll just count by ones, and I'll show you why in a second. Y equals 1. That's the midline. Now, I have to have a stretch by 2. So instead of just going up 1, I'm going to have to go up 2, or in this case, I do have to reflect over the axis. So normally for sine, you would start here and go up 1, but we're going to have to go up 2 And also we're going to have to reflect it. So instead of going up 2, we're going to go down 2. So I think our second point goes down there. Let me erase these. So again, it's a sine curve. So we start right on the midline. It's reflected, so instead of going up, we go down, and there's a vertical stretch of 2, so we're going to go down 2. And then it's going to come back to the midline, then it's going to be 2 above, then it's going to be back to the midline. Connect it with a dotted line. Fill in the back. All right, draw in your asymptotes. So we're going to separate them, the hills and the valleys, every time it crosses the midline. And then reflect the hills and valleys. Awesome. So now you guys are going to try Unit 3, Practice 3, more graphing. Trying to do all of this by hand, right? Your goal is to do this all by hand and think through it mentally. So good luck. If you need help, let us know. Have a good day.